Wagwan, and welcome back to another episode of Kevin Does Physics. Today we are continuing topic 3 by looking at topic 3.5, which is all about Newton's laws. I believe this used to be part of the A2 syllabus before a syllabus change in 2015, so if you're looking for past paper questions on this topic, go look in the A2 papers. Onwards, yes, I keep messing that up, but anyway, Newton's first law. A body will remain at rest or continue to move in a straight line at constant velocity unless acted upon by an external force. Yeah, so basically, unless you push something, as I've just pushed a water bottle off my desk, I mean, it was happily sitting there, it had no issues. I applied external force, it wasn't at rest anymore, it gained velocity. Good. Newton's second law. The resultant force on an object is proportional to the rate of change of momentum on the object, and the change of momentum will take place in the direction of the force. So basically, that is the written way of doing it. The formula for that is, of course, F equals ma, because ma is basically ma is the rate of change of momentum of an object. And on to Newton's third and final law. If object A exerts a force on object B, then object B exerts an equal but opposite force on object A. And Newton's third law is possibly the most difficult. I mean, it's the most easy to trip up on, because there are sort of two things you have to know, and that is that the forces must be the same type, as well as the forces must be in opposite directions. We know that, but they must also be on different objects. Onwards. So next we're going to look at momentum. Momentum is mass times velocity. All moving objects have momentum. Like an electron has momentum, it's going to be a reasonably small amount of momentum, even if it's travelling near the speed of light. But, I mean, yeah. Momentum is, of course, a vector quantity, because velocity is a vector quantity, so it remains a vector quantity. And in collisions, momentum is always conserved. Whether we have an elastic collision or an inelastic collision, the momentum before the collision will always be equal to the momentum after the collision. And that is for a system. So let's say you throw a ball against a wall. It comes back to you. Technically, the wall weighs a hell of a lot, but it will still have moved a tiny little bit and will have a tiny bit of momentum. Impulse. Impulse is measured in Newton seconds and is equal to the change of momentum of an object. So, for example, if you throw a ball at a wall, let's say it weighs 1 kilogram and you threw it at 1 meters per second, it has a perfectly elastic collision, so it comes back to you at 1 meter per second, so the coefficient of restitution is, of course, 1. That would mean that the change of momentum would be 2 of those units, with 2 of those units, and it would then come back at you. Basically, it means that it's had an impulse of 2 Newton seconds. Yeah, I sound confident, don't I? Elastic and inelastic collisions is the final part for this episode. As I said before, in both types of collision, momentum is conserved. No collisions are truly elastic, but as we learnt in topic 5.1, we presume the most elastic we can really get to is collisions with gas particles, and for an ideal gas, we presume that all collisions are perfectly elastic when they're only almost elastic. Because always in a collision, some energy will be lost. In an inelastic collision, which is basically every non-theoretical collision, momentum is conserved, but the kinetic energy is not. So that means that some energy will have been lost to sound, thermal energy, whatever. But of course, in the system, energy has still been conserved. It has just been converted between different types. Thank you for watching, and bye-bye.